to make sure that the stream is working. Okay. Um, we're gonna cover some good stuff. Like I'm pretty excited about today. But I do want to make sure that my video from this morning was
You get through this class. We need to talk about motor control side.
okay. Okay, so it's just on a lag, but it should be working. Let's see if I can't make that bigger, because I'm going to use every circuit, which we haven't used in here yet, but it does better about like the
I know you're focused on that, but after talking about like AC and DC motors, don't forget next week we could go into the reversing motor section. I'm trying to work my way through this before a little bit ahead of time.
all right. Is that any bigger or is that the same size? But not. All right.
Yeah, before it was like equal size. It's half what we call it.
All right. So let's see. That's back to the regular size it was before. Have to. Is that better?
Get over to the side. It's half.
All right. We'll see if we can keep that going. If it starts messing up, let me know and I'll try to fix it. But hopefully we won't have any issues.
This week, did see what on
Do what now?
our lab, did see this week? Is it on?
It's going to be on both. You're going to do a couple of things in every circuit, and then you're going to put them on the breadboard and measure voltages to make the voltage drop, right? So you're going to get to physically do
So I need to be more for my lab.
there's a physical component to it. So whenever you want to knock out that physical component, all right, so now it seems like we are jumping around the book because we are, okay? Because there's a whole lot of stuff in the book that isn't as important as the stuff that we're covering, okay? So we'll be in chapter 9. And we'll stay here pretty much the whole time, okay? So read through chapter 9. All right, so let's build a circuit. We're going to use every circuit when you're watching this video or doing whatever, you'll be able to redo the circuit. But on page 225, on figure 917, we've got a transistor as a switch. All right, so I'm going to scoot over here. I want to get an NPN transistor. I know it's an NPN because the little diode is pointing out instead of pointing into the base. Okay, so let me zoom in a little bit. Y'all see that? All right. So, so we've got, it won't let me draw on top of this, but we've got an N channel, P channel, and N channel. Okay, and that P channel is the odd man out. It's in the center, and by putting current through there, we can open up a bigger gate. Okay, so what I'm going to do is a light emitting diode, an LED, is just an LED. It works in the same way that the diodes work that we talked about beforehand. But when you do have that cascade over, it emits a photon. Okay, so it looks just like a diode, but then it's got two arrows coming out to show that it's letting light out. Okay, everybody see that all right? All right, so I'm going to put a resistor in series with my base. All right, you could think of a base as like a gate, or like a gate. Now in FETs, like field effect transistors, they're actually called a gate. Okay, and we'll talk about their differences. But the vast majority of what we do in here is deciding to let current flow or not based off of a decision somewhere else. Okay, and when we get into programming, like let's say a PLC, in the PLC we'll have two switches and then a light, and if we push both those switches, light comes on. That's a fundamental AND gate in logic. Well, we don't always want somebody to have to push 500 buttons to make that happen, so we can cascade these things, and we can make a million transistors on a small wafer, and they can be wired up to make these decisions for us. So what we're building right now is a switch. Okay, so what'll happen is as I wish it would let me draw on top of this. But as I dump things through, like as I let current flow through that base, that middle part, I can let a much bigger current flow from between my collector and emitter. Okay. So one thing that's not on the schematic uh, on the book is a resistor to keep the current low on that the LED. We don't want the LED burning up, so we're going to put a little resistor there. Depending on what resistor it is, or depending on what diode it is, you know, we might need anything from, you know, 300 to 1,000 ohms to keep that current low enough. Most of them can only operate at like 20 milliamps. So depending on what the voltage source we have, and depending on the voltage drop across that diode, which that voltage drop across the diode from the voltage source, and then we would be able to determine the current. And if the current's more than 20 milliamps, that diode's probably going to burn up. Okay. All right. Now we're going to put a voltage source. Like we deal with a lot of 9-volt batteries and stuff, and 12 volts and 24 volts. So let's just put this at 10 volts because they'll help us like with math later. Okay. All right. So I'm going to connect 10 volts up here. Okay. I'm going to connect that 0 volts down to the ground. All right. Now, if I put a voltage on that base, I can start drawing current through that base, and then it can open up the big gap, right? Now, if I run this right now, I don't have any current flowing because that junction between the collector and the base and the emitter is not letting anything flow. Okay. So I'll pause that. I'll go back to edit. And what I'm going to do is I'm going to put a little switch in there. Okay. I'm going to connect it to my base. I'm going to put another little resistor there. Let's make a voltage divider. Okay, so let me delete that, or let's just move it over a little bit. All right, so we'll move that over a little bit. We're going to make a little voltage divider. Okay, we're going to put 2,000 ohm resistors. We're going to connect it. And are y'all all in DC? Like if I have 2 of the same resistors across a voltage, then I'm going to drop half of it because it's dropping them equal. All right, so I should be getting 5 volts at that junction right there. Oops, that's not the one I want to do. I want that junction to go right there. So if I open and close that switch, I'm letting 5 volts and the current that's going to flow through there open up or close that bigger flow. Okay. Let's see if I'm right. All right. So I still have nothing going through the big side, right? But I do have current flowing through that voltage divider network. Now, depending on the amount of current that I let through that base, once I flip that switch, booyah. Right? And you're like, wouldn't it have been easier just to put the switch on the diode? Well, yeah, but we wouldn't be able to, we're not going to have little miniature people in there pushing switches. We're going to use like the outcomes of other things to dictate if that's going to come on or not, right? So we might have a switch down here. If this green light is on and this green light is on, then this needs to be on or something, right? So we'd be feeding from this network, and instead of having a physical switch, we would just use that transistor, okay? So I can turn on that that LED by flipping that switch. And what happens is I get a little bit of current. If y'all look at that base current right there, a little bit of current right there. I've got 2.7 milliamps that is controlling near about 20 milliamps. Okay. Now, since I know that diodes die usually around 20 milliamps, I was really close with my 400 ohms. Let's burn out that diode real quick. Like if I drop that down right there, now the current's more and it burns out that diode, right? So just by doing it a lot, I knew that I probably needed at least, probably 400 ohms. And that's really getting close to that's going to make it the brightest, but it's also going to make it last a lot less time, okay? So the thing that I want you to pay attention to in chapter 9 is the fact that bipolar junction transistors, BJTs, are current controlled devices, okay? That there's some amount of leakage current. Y'all see this current that's going back into the voltage divider? Y'all notice before I flip that switch, I have 5 volts on that voltage divider, right? Give it a second. 5 volts. Why did it change right there? Because now I gave another path for current to go. So that's going to add to my voltage divider circuit. Okay. Like, so that part that I just added is pulling that voltage down because we got more current that's going through this way. Okay. Does that make sense? Like we've got another 1K ohm, and then whatever that resistance for that junction is, that is basically putting something in parallel with that 1K ohm resistor on the bottom. Okay, so when you have current going through a different part of the circuit, you can have that where you're pulling down that voltage divider. When we load things onto there, that voltage goes down because there is more complex things that are happening to it other than just, right there, we have no current, going in or out of there. We got 5 volts. If you plug in a 12 volt power supply and then you put a load on it, a lot of times if it's not regulated really well, that, I hope this is loud enough. I forgot to move my microphone. A lot of times, like, you might have 9 or 10 volts because it's pulling down that voltage divider. Okay, we can make that more powerful, or filter it more so that those little sags and stuff don't happen, with capacitors and stuff that we'll learn about. But what questions y'all got now? We can use a little current to make a bigger current move. That right there is called amplification. Okay. This is, y'all saw the little, orange cream guitar pedal that I built, right? I'm going to show you the schematic for this. Okay. All right. So that is a circuit I designed for the guitar pedal. You put a sine wave in from a guitar. Like when you strike a note on the guitar, it vibrates across these little pickups. They're just, a coil with a magnet on it. And the change in magnetic field looks like a sine wave. And then whenever it gets into that circuit, like what happens is we're able to amplify it and we're also able to clip it. Like, so if the sine wave is going up like that, if we amplify it too much so that it can't get any higher, it'll hit a roof and then just straighten down. All right, and you can get a lot of harmonics, and that's where you get the distorted sound from. Okay, so you're looking at, a pretty good guitar pedal. Like it sounded like Eric Clapton. Like, go look at the reviews for it, like where people played it. Like that little circuit made it so that you could, sound like Cream from, like the Disraeli Gears time. And all it is some diodes and some transistors. All right. Now I want you to look right here. Y'all notice how I had to put a switch in there and then had to make a voltage divider to get my bias voltage for my base? All right. You do that some, but you can use the same voltage that you're controlling, or that you're using to, like, the big current side. You can feed a little bit back off of that, and so that 100k ohm resistor right there is called a feedback resistor. All right, so what that does is that takes stuff that's going on up there and it feeds it back into the base. Okay, so the 10k resistor and that 100k resistor, like, I'm going to put it into I'm going to tell y'all where to look at it. Okay, so it'd be like a collector feedback circuit, like 924 on page 231. And so you're taking current from the collector, feeding it into the base. All right. So let's build one of these. All right. So y'all are going to do a circuit in here. Have y'all used every circuit? Okay. So I want y'all to do it in here because, like, on Tinkercad, it doesn't show what's going on inside of the circuit really well, right? Y'all under, like, I'll go over, like, using the breadboard a little bit easier. That's going to be part of what I'm talking about today, to prep you for what we're going to do. But instead of using Tinkercad for this, I want y'all to use every circuit, okay? Because it's going to aid in understanding what's going on. All right, so this circuit I want y'all to build. You will take a NPN, all right, and you're going to feed back some of the current that's going through there back into your base. Okay. We're going to keep it simple here, and we're just going to put that base at 0 volts. Can y'all see the circuit so far? All right, what this will do is it'll make it. Now let's make a amplifier. This is an amplifier. So, like, this would work, like, when you plug that string and it moves that magnetic field, that pickup is only putting out a, millivolt level signal. Okay? So we have to amplify it. All right? Now, BJTs aren't the best way of doing that because of that leakage current. It's a current controlled device, so some of that current that you're making right there is getting wasted, and it's going to give you a voltage drop. Okay? If you have something where it's not a current controlled device, like a FET, like a field effect transistor, there's no current going through that gate. So it doesn't matter what your voltage is, because it could be a mile long worth of resistance. If you've got infinite resistance right here, you're not voltage dropping across there. When you've got a current controlled device, you are voltage dropping. Okay? So that millivolt signal might not be strong enough to make this work, because you've got a voltage drop across your cable. Okay? That'll make more sense when we start talking MOSFETs and JFETs and all the field effect transistors. Okay? But they're still a variation of the same. The only downside of BJTs is it's a current controlled device. Okay? Just remember that. All right, so most of your guitar pedals have a 9-volt battery. Okay, so we're going to use that as our DC power source. All right, so we're going to connect 9 volts to there. We're going to connect 0 volts to there. All right. Now let's make a guitar. All right. So, does anybody know what like A is? Like the A note is some multiple or division of 440. Okay. Like in concert pitch, 440 is an A. I think it's right below middle C. 880 is an A. Every time you double it, you got an octave. And then 220 is an A. It's an octave below. So let's put it at that 440 hertz. So I'm hitting that like second string on the guitar. So I'll take it down to 440. Cool. So that's my guitar plugged into there. All right, now I don't know how this will react right now because we do have capacitance that decouple the two things. Let's see if we can get away with not using it right now. So I'm going to plug in one side of my guitar to that bass. Okay. And then I'm going to plug in the other side to the ground. And let's see what happens. Okay. All right, so we're clipping pretty hard, but let's see if we can't add some things. One of the things that we can do is I want to add, y'all know how on the orange cream schematic I had the sine wave and all that you could see? Let's go and put, I want to look at that node right there. So I touch the little eye. I want to look at what's coming out of my guitar. So I'm going to touch that little eye. So that's a green one. Okay. So I've got a blue node. Okay. I've got a green node. So we're going to compare what the two look like. Okay. So we've got that sine wave, right? And we've got a pretty hardcore clipping thing going on. Okay. The reason that is because we use a 1K and a 1K. All right. That proportion is going to tell me how much I'm feeding back to that bass. I want to feed back a little bit to that bass. Okay. All right. So what happens when I go up? When I go on a positive side of sine wave, that's actually opening up that gate, right? Which is making it go closer to ground, right? So as I go up, I'm going to have an inversion of what's coming out of there. So when I get this not clipping, what's going to happen is that the sine wave, when it goes up, the output's going to go down. And when the sine wave goes down, the output's going to go up. When you have one transistor, you can amplify it, but you're also inverting it. Okay? And before I change everything, I want you to understand why. Look at that blue node. When I start putting current into that gate or that base, that opens up that transistor. Imagine that transistor is either open, like infinite resistance, or if we turn it on far enough, then it's zero resistance, right? When we talked about those voltage dividers, the voltage was proportional to that resistance, right? So whenever I have a high resistance, that voltage divider between that transistor and that 1K up top, imagine I had 1K up here and then 1 million down here. It's going to be a high voltage, right? That's whenever it's off because it's not turned on. So we've got a very high resistance, right? What happens as I start turning that transistor on? That voltage starts dropping. Imagine that transistor is all the way on, so there's no resistance. So that'd be like 1K with a 0K or 0 ohm resistor down top on the bottom, right? Y'all follow? Like, so imagine that transistor changing its resistance, okay? So when it's off, it's real big resistance, and that 1K is nothing compared to it. So I'm going to drop most of my voltage across that transistor. But then as I start turning the transistor on, that voltage drop gets smaller, because as I turn it on, it's like I'm connecting it directly to ground, ain't I? Okay? So let's change, let's do a different proportion. Let's do a 10 to 1. If I had a 10 to 1, then that means that for every 1 volt swing here, I get 10 volt swings on the other side. Okay? Let's see if, so let's put that up to 10K. And that should start helping us out a little bit with, give it a second. All right, so we still have a little bit of an issue. And one of the issues right here is because this has a it's affecting the other part of the circuit. So y'all haven't learned capacitors yet, but we're going to throw one in. What capacitors do is it lets the sine wave go through. It lets high frequencies go through, but it blocks low frequencies. So the little bias voltage that sine wave has, I didn't expect to have to do this, but we might as well go ahead and do it right now. Like, you learn a lot about capacitors and AC, but the only thing you really need to know about them right now is it's going to block the DC component, like, of my guitar signal. Okay, so I'm gonna connect that up, same thing, but it's blocking the DC. All right, so it's going to make it so that we're okay. So I need to add another. All right, so those will start. It might help if I connected those two together too. Come on. I think I broke it, Jim. Give me just a second. I'm gonna kill that. I'll add one more. Let's go ahead and put that there, that there, that there. All right. We're going to take that down to 440. And then we want to look at, well, let's take that orange off so we can just look at what's going on here. All right, so we still have some clipping. What we'll do is we'll make that that gap bigger. Okay, so let's put 100K here. and give it a few. All right, so we're amplifying, but still not a pretty thing. Like when you get that little hook right there, it's putting harmonics in that weren't there to start with. Now for a guitar pedal, that's a good thing. Like it makes rich tone, stuff like that. Distortion. But what we need to do is we probably need to get this right here so that it's not touching ground anymore. Because what happens is it gets so low, it can't go any lower, so it's not going to be able to follow everything. Okay? So we're going to take this, we're going to cut it, we're going to add one more resistor. And what that's not what I wanted. That should do it. All right. Let's smooth this out some. See if there's a I figured out what I did. All right, so the feedback needs to be a small amount, okay? That doesn't mean it needs to be a small resistor, right? So I flipped what I should have done, and I had a big resistor restricting the total flow, and then a little resistor restricting back to the base. So that resistor needs to be really big where the other resistor does not. So what we want to do is, and this was a mistake on my part. So I'm not always perfect. That's what we want to see. Once that starts filtering out, we should start seeing those two signals are out of phase with each other, aren't they? Like as my input, my green goes, my blue goes almost completely opposite of that. Okay. And that makes sense. As I start going up in voltage, I let the base let stuff through, which makes that go closer to ground. All right. Now, I probably didn't need to put this in there to bias it. So let's take it down to near about nothing. And we should be, well, we're going to hit the ground a little bit. We'll just adjust this until we're getting where we want. All right, so if I've got 10K there, let's take that up stupid high. Like the bigger the proportionality between my feedback resistor and my other resistor is going to dictate how much of a multiplication I get. So if it's like it's 100 to 1 right now, so as I go up 1 volt, if I go up 1 millivolt, it'll go up 100, or it'll go down 100 millivolts. All right. So we'll take this and we'll put it back to maybe, half that. So once that filters through, we'll start seeing the swing on there. All right, we're still kind of clipping, aren't we? We're going straight on the down slope. So we'll make that even. We should start getting a cleaner signal as we go. Okay. Now, I told you that a capacitor takes the DC component out of a circuit. All right, well, what I'm talking about is, you see that blue? It is it's not going around zero, is it? Green is. But blue is superimposed on top of like probably 9 volts or so. It's going up and around 9 volts. So what we want to do is we want to add another capacitor to get that DC component out of there. And then we're going to see what that looks like. I'm going to add this right here, and then I'm going to put a node there that we can watch. So now the orange is going through the capacitor, and we're going to strip the DC component out. So it should follow whatever blue's doing, but be down there where the 0 volts is, okay? Oh, I actually need a resistor on there too. All right. So let's this is part of our filter. And once we get this right, this is a circuit that you'll build. And you'll be able to see it on the O-scope. All right, so orange is doing the same thing blue is doing, but we strip the DC component off of that, right? Like the DC component is going to bias it up or down. Well, if we want to feed this into a different circuit, right, we need that DC component off, because y'all remember when I had that DC component on the sine wave, it threw all my voltages off a whole lot, right? So once we do this, we need to filter that back out, because we put that 9 volt DC offset on there when we did this with 9 volts. Okay, cool. So since we injected it with DC, we need to get that DC out. All right, so now y'all haven't been in AC fundamentals yet, so I don't need you to know anything about the capacitors other than the fact that they let higher frequencies through real easy, but they don't let low frequencies through. Okay, the way it does that is, let me draw this out. All a capacitor is 2 parallel plates. Okay, if I put an electron over here and I put it onto this plate, I can store electrons on there. Okay, but it can't get over that gap. All right, there's what's called a dielectric, and it's not supposed to get across that gap. The electron cannot get across that gap. Okay, now the interesting thing is that gap's not too far for an electron to affect another electron. So what happens if I put an electron over on this side? It can't jump that gap, but if I hit an electron on that plate, the like charges repel. The repelling of it can I have a little force field around it, right? So imagine I've got a guy, he can't jump over the gap, but he's got a big old ball around him. And whenever I go over there, if there's another guy with a big old ball around him, I can knock him back, right? So even though the electron cannot jump that gap itself, it can cause things on the other side of the gap to happen, okay? Now, when I first turn on or put stuff into a capacitor, I can fill this up with electrons, and then if it's DC, there's a certain point where nothing's going to cross, right? Okay. Now, when it's AC, that means that at one point I'm putting them in over here, and then at another point I'm putting them in over here. So with AC, I'm charging up one side with a bunch of electrons. And then I change directions. There's no electrons over here. I start putting electrons over here, and their force field makes an electron go out here. So even though it's not the same electron, like with AC, it looks like it is because I put one electron in and I get one out. Even though it's not the same electron, I get current, right? I get a moving electron, one in, one out. So I start filling up this side, and then another one comes out. And like, so these aren't there anymore. Fill up this side. Boom, right? As long as I got my frequency to a point where I'm not filled up on one of those plates and then empty on this, right? Like by the time I get done with that, if I don't change direction again, current stops again, right? So AC means that I'm going back and forth. So with an AC signal, I have a pretty good, like, it's changing directions quick enough that I'm not running out of electrons on those plates. So to us on the outside of that capacitor, it looks like alternating current doesn't have a problem going through there. The faster the frequency, the easier it is for it to go through there, even though the actual electron that I put in isn't the one coming out. Okay? It's like I'm ping-ponging them. I'm put one in, it slings one out. Now I'm putting that one back in, it slings one out. Now, if it was DC, I would charge one plate and then nothing would happen. So lower frequencies, it looks like a gap, and I can't get over that gap. Okay? So whenever I did this, like whenever I put those capacitors on the input and the output, I took that DC component off of there so that I could use it later on, right? Like, so that it wouldn't wreck the other part of the circuit I'm trying to do. Because before I put those capacitors in, I had to know what the input impedance of that sine wave was. I needed to know what the DC offset voltage was for it and stuff, right? Now, from a guitar, it's around 0, but if I had something else feeding into this, it would be something else. And I don't know how to get to where I can set a DC bias, right? That's just changing the frequencies. Okay. So to make a amplifier circuit, we are going to have to strip DC components off. So you'll have a couple capacitors, and they just look like, you'll see them. I'll show a couple examples of what they look like. You're going to have a breadboard, right? We'll probably use the same breadboard y'all used before, okay? Because it has a bunch of things on it that we can use. You'll run through a capacitor. Let me show you what capacitors look like. And when I tell you that they're parallel plates, right? There are capacitors that like are really big and they have big old plates and they're straight like this. All right. Now that's not the most efficient way of getting a whole lot of surface area into a small space. So most of your capacitors, what they do is they'll take a piece of foil, they'll put, like, let's say a piece of wax paper in between it, and then they'll put another piece of foil, so they'll make a sandwich. And then they'll roll it up like a fruit roll up, right? And then by rolling it up, those plates are still parallel with each other, even though they're curved. And we're able to fit a whole lot of surface area into a small little area, Okay. Um, so, just because they don't look like what their schematic looks like, y'all know the schematic looks like two parallel plates. They look like anything from like this little tantalum there to this electrolytic here. A lot of what we'll be using would be like these little film capacitors like this, and if they're really small, like picofarads, they'll be ceramic, kind of like that little dude there. I'm going to do something for y'all just to prove that. Let me get it. Clippers. All right, so we've got a capacitor that looks a lot like one of these. Okay, so we got a little round thing. Looks like a little water tower or something. Okay. Now, if y'all do come across a $200 Leatherman multi-tool, like it's one of the new nice ones, and it happens to have spears engraved on one side and then of the knife, and like an electronic circuit on the other side, let me know. I'll put a reward out for it because it's that important. Like my wife and my son got it for me for Christmas, and I can't find it, and I don't know. Like it had a problem with falling off my belt, so it could be anywhere. But if you happen to see it, like if you're watching this online, if you happen to see it, you're here, happen to see it, like I would be ecstatic about finding it because it was about the nicest multi-tool. It was one-handed. Like I don't have fingernails because I bite them. All right, all I'm doing is taking the plastic off of here. Okay, I want y'all to see there's nothing magical, right? Like I want y'all to correlate that even though this looks a little different than what the schematic looks like, that it's still just two parallel plates, a whole lot of surface area. Cool. I'm gonna try to do this without cutting myself open. Because that little can, it's sharp when you start peeling it away. All right. So there is a can around it to protect it. But now, take the little rubber piece off and one terminal is soldered to one of these little foils. And the other to the other. Trying to get it so I don't. There we go. There we go. All right, so you get two metallic films, right? One of them soldered to one leg, one of them soldered to the other, and they're placed together with a dielectric material. Dielectric means that, you know, electricity shouldn't go across it. Like, it might be oil impregnated paper or whatever. But at any rate, it keeps a gap between them, so they're, you know, the electrons going in aren't the electrons coming out, right? And they just roll them up so that you can fit a whole lot of surface area into a really small form factor. Okay, so there's nothing magical there. Like, I don't like throwing a whole bunch of extra stuff at you, but I think a capacitor, it's going to be needed because we're going to be doing a lot of things in the frequency. Is that how you say that word? You ever think of a word too much and then all of a sudden it doesn't sound right to you? Frequency. We're going to start doing a lot of things in the frequency domain. And so you need a little bit of this, okay? So come in, verify what this circuit should look like. All right, so build that up. All right, and then you're going to use one of those beige. Y'all know when y'all use the signal generators so that you can make a sine wave so you can see that the rectifier was working. You're going to use that for that 440 hertz. I don't really care what frequency you put it at, but then let's say that you use that. I'll get some batteries for them. You'll go from the 9-volt output to get your DC bias voltage. You'll use one of those, I think they're 2N2222s, which are NPN transistors that I bought. You'll wire them up like this. Now, how do you know what pin is what? They're different on different transistors. So look at the number on there and Google it, okay? And then you'll get something that looks like this. So you'll have a flat side, and then you'll have three terminals. And depending on what type of transistor it is, you know, the base might be here, the collector might be here, and the emitter would be right there. And so you'd follow it based off of the flat side of the transistor. Okay. Sometimes the base is up top. You know, it depends. So just because a schematic looks like the base is in the middle doesn't mean that that's the pin. Okay. Like, the schematic's always going to look like this. And then dependent for an NPN, and depending on the pin out of what you Google, like, you know, it might be base, collector, emitter. You know, there's a ton of, well, there's 3 of them. There's 6 combinations. That can be 3 times 2 times 1. I think that's correct, right? How many combinations do you have? Yeah, okay. So when you get that transistor, Google what that transistor is. So let's say if it is a 2N2222. Google it. Go find a schematic diagram for it. It says 1, 2, 3. 1 would be the emitter, 2 would be the base, 3 would be the collector, right? And look in your book to see which one of these is your, base. What did we decide? The emitter was down here. Emitter, collector. All right. So depending on that, you're going to have to do that because I want you to get used to taking a little bit of information and getting a lot of information from it. And part of that is being able to Google data sheets. Okay. So just Google whatever's on the face of that, or if you're lucky enough to get the box, it's an NPN. So these are, this one in particular is a 2222. Now, I'm not promising that, well, on the back of here, it has things. But I don't want you just dependent on this. I want you to find a data sheet, okay? Actually, I think in the lab, I should take a picture of the data sheet. Y'all know how to take a screenshot? Mm-hmm. All right, so take a screenshot of the data sheet, and that's going to be part of what I want you to turn in. Are y'all comfortable with how to wire things up in a breadboard? Let me go over that real quick, because there were some people who weren't. Okay. All right, so you got a breadboard. There's a gap across here, and that gap makes it so you know that there's not connections between like this row and this row. Okay? That's so that we can put what's called dual inline like dip packages, so they look like what you think of as a chip that has a bunch of things like, like maybe 8 pins over here and 8 pins over there. And those 8 pins on either side aren't supposed to be connected together, so we've got that little trough so we can put stuff in there. Okay? I hate when I do that. I try to do it on separate layers so that I can just delete what I draw without having to do that. All right. So if you want to put a capacitor in, all right, what row you put it in doesn't really matter. All right, so let's put it in that row. Let's put it in that row. And then let's say that it looks like one of those big, capacitors, right? If I want to connect something to this part of the capacitor right there, I need to put it in the same row. Let's say that I had a resistor or something going off of there, right? I need to put it in that same row for them to be connected, all right? So this row right here, all 5 of those are connected on the inside. So if I put anything in any of those holes, they're going to be connected. Now they're not connected to anything in the row beside it, right? So those 5 are separate, okay? Now across the bottom and across the top, we have a row down there that is all connected. There's like 50 holes there. Because there's a lot of circuits that there's a lot of things that connect to certain things, like our power supply. Like a lot of the sub assemblies in a circuit all need like maybe that 12 volts to operate. So there's nothing special about like the top one versus the bottom one, But since they do label it, you might as well use that. So like, I would say like I would plug in like my 12-volt battery and put the positive part to that top one right there, right? So that I remember that there's nothing special about it, but since they labeled it that way, it'll help me remember it. Now, this red up here and this red down here are not connected unless I put a jumper across them, okay? If I need more than 50 holes, I'm probably going to put a jumper over there. Or if I have stuff up top and on the bottom, instead of running long wires down to the bottom from the top, I'll probably just run one up there to feed, you know, shorter wires coming out, okay? On the O scope, last time you used one one lead, y'all just had the yellow, right? You're going to need two of them. You're going to put one on the input. So put one as close to the signal generator input as possible, right? So that's going to show you what you're putting into the circuit. And then put one like at that orange and at the 0 again. So both of the leads from the O-scope, the little alligator clips are going to go to ground. Both of them are going to go to ground, right? And then the yellow lead, like the first one, put to your input. So you see what the function generator is actually putting into the circuit, okay? And then on the output, put the blue lead, like the one that's going to the blue side, okay? And we should see something like that orange and green going on, okay? Now, I know everybody in solid state are not in DC. Might behoove you to go over color code, okay? Because you're going to be digging through that box, and you're going to need to find two 1Ks and one 100K. All right. So one is brown, then 0 is black. So you'll have a black or a brown black, and then for the 1K, we've already got 1 0. We need two more, right? So that'd be a brown, black, red. All right, for the 100K, we need 2 extra zeros past that, so 4. So red, orange, yellow. So it'd be black or brown, black, yellow. Cool. I think that's right. That should give us 100K, shouldn't it? 100K is 1 0 and then 4 zeros. Red is 2, orange is 3. That ain't right, is it? 100K, 3, 4, that's 5 zeros, right? One of them's already taken care of with the second one. When in doubt, I've been doing this for 20 years, and you know what I'm going to do? 100K ohm resistor color. Brown, black, yellow. Now, I had to memorize this. Like, had I not gotten a tattoo, I could have had it up there and checked. Because when I learned this, we didn't have easy access to the internet. So I have to change things. I don't think that, like, memorizing brown, black, yellow for 100K is worth your time. Right? I want you to get the gist of it, right? But these type things are readily available to you, right? So I don't want to waste your time forcing you to memorize everything so you could break out, oh, well, that's a brown, violet, brown, right? But I do want you to get the gist of it. I don't want you being like, oh, I don't know what, like if you needed to figure it out, you could figure it out. But as far as wasting time on it, I don't think it's worth it. So you still need to find those resistors. I'm not counting off if you use an app, right? All right, so well, let's do this. I'm really good at it because I teach it, but if I went back and filled, you know what I'd do? I'd get me one of these. All right. There's 50 million apps. All right. And I'm of the sort that you are important enough not to languish with things that are easily. I don't know if it was Einstein who said it, but somebody was like, do you know the speed of sound? And he's like, why would I memorize that when it's readily available in books? Right? Like, why memorize? Why waste your time when you can do higher level stuff like building a circuit by getting into the minutia of that? I've got a buddy who's the best electrical engineer that I've ever met. He's colorblind, so there's no help there. Like, he got bad grades in DC fundamentals because they were like forcing you to have to do stuff like that when he's colorblind. Do I think somebody who can tell you right off the bat that, you know, brown, orange, brown would be whatever it is? No, because I think I'm a really good, you know, dabbler in this technology, and I can't do that. Right? I can sit down and start going, okay, and that's kind of where I want you. Like, if you had to know it and you didn't have service or something, that you could figure it out. Right? But y'all will have to go fishing for your resistors, because I'm not going to give those out. Like, I'll put some capacitors and some transistors on there so everybody's using the same. But if you get the wrong resistor, it's probably going to look funky. Okay? It's probably not going to do what you want it to. So, what questions y'all got?
Back on the circuit you made,
Mm-hmm.
you said that you were like removing the DC component.
Mm-hmm. Okay, so, like, you see that blue line up top? All right, so that's a sine wave, and that's exactly what we're putting out of that transistor, but it's got an offset to it. Instead of going around, it's not an AC signal anymore. It's all pushing. It's pushing heavier, and then it's not pushing as much. All right, now, when I put that capacitor in, you notice that it took that offset off of there. So that orange is that blue, but without the DC offset. Okay, so it's not going around that 9 volts that it was before. It's going back around to 0 volts. So now we are getting a push and a pull. All right, so that's important, because if we fed this into a different circuit, if we had a DC offset on there, then all the math we did to figure out the amplification factor and the frequency response and stuff would be screwed up, because we had that 9 volt offset on it. Okay, because now ignore that it's running right now. Okay, if I didn't have that, these caps are called decoupling caps. They decouple what comes before and what comes after. Okay, that's important, because if I started adding a circuit right here, let's say that I had it going into some other resistance, right? If I just had a line where that capacitor was going into there, it's not just dealing with the math that I have in that part of the circuit. Because all of a sudden, if I don't have that capacitor to block the DC component, like, basically, let's cut that out real quick. Let's cut that out. So if I had it coming out straight from here, now the stuff that precedes it, that 1K and that 100K, make part of a more complex circuit that I have to deal with in the subsequent stuff. So right here, if I like with this 1K right here, like let's say I had another voltage divider here or something, right? If I didn't decouple it, then this 1K right here and this 100K right here would become part of the equation. Okay, because you see that they're making a complex circuit there. The capacitor makes it so the DC component's not going back and forth. So we don't have to deal with anything behind that capacitor when we're talking about making the net circuit, right? We're just dealing with another sine wave, and none of that DC component is going back and forth, so we don't have to factor that in, okay, into those equations when we're trying to make that second part of the, let's say we make another amplifier circuit that's going to take that 10 to 1 into another 10 to 1, so now we're amplifying by 100, right? If we didn't have that decoupling cap there, then all of those resistors would be part of that circuit that I had to, like, I couldn't. Right now, this is a standalone piece of a circuit. If I add other circuits that decouple too, all I have to do is look at those pieces, and I don't care what's going on in these as far as the DC component's concerned, right? So I don't have to factor in that big network of all those resistors. I just have to factor in what's inside of those capacitors, okay? Because, like, if I don't have that capacitor there, I could have something funky with the resistance, and then all of a sudden, even though I'm got stupid gain over here and it should work, all of a sudden I'm getting shorted down here with this other resistor that's a really small comparably. So it makes a much more complex thing where I'm having to factor in all of the resistors all at once to figure out what's actually going. Where if I decouple it and I break it so that that capacitor is basically, those two resistors aren't able to really see each other on a DC plane, right? Because there's no current going between them. So I'm not screwing up like my voltage divider by having other voltage dividers over here. That capacitor, it takes out the DC component, and it also delineates, it puts a gap where you say, okay, everything here I can work on, get it right. And then no matter what I do with what I plug into it, it's not going to affect this math that I already did. And that's not going to affect the math that I need to do over here. It'll start making more sense when we add another component to it, like we make another circuit that this is feeding into. Because the problem with those being out of phase is if I try to listen to both of those at the same time, they're canceling each other out, right? They're 180 degrees with each other, so they're canceling each other out. If I had a guitar and I'm running into two different things, like I'm running parallel, and one of them puts me 180 degrees out of phase and the other one doesn't, then they're going to clash together, and it's going to make my guitar sound really weak, okay? So we hardly ever do something where we invert it without inverting it again. Okay. So if I wanted 100 multiplication factor, I want it to be 100 times as loud. Instead of doing it with one circuit like I'm doing here and doing 100 to 1, I would do it like a 10 to 1 into another 10 to 1, because it would still get the 100 multiplication, but it would invert it, and then it's going to invert it again. So whenever it comes out, it's in the same phase as what it went in. Okay. Like, so when my AC signal is going up, the output's going up. Right. So that's one of the problems with the out of phaseness. By inverting it, like, you get nodes. Like, you know, if this is pushing and this is pulling at the same time, you know, imagine we had two speakers. All right, and one's pushing while this one's pulling, and this one's pushing while this is pulling. That makes like this weird node thing where you're not getting the full power out of your system. Like if it was perfectly balanced, you wouldn't get any sound out of it, right? Because like they'd be canceling each other out. Does that make any sense? So by decoupling with the capacitor, we're taking the DC component out, which makes it so that it's a lot easier to make a different circuit to butt into this one. I don't have to look at them as one thing. I can make this one perfect, make the other part perfect, and since they're decoupled, they're not affecting each other as much as they would be if I didn't have it decoupled. I'll try to come up with better ways of, or another examples of why we'll do that. And while we're experimenting with this circuit, y'all gonna build this circuit, right? While y'all are experimenting with this, we can do it with or without caps and see the difference. All right, at least this output cap. I think we're gonna get too squirrely on that input cap. I will probably keep that in there too, like for the whole time. All right, so this is like, y'all can pull this up. I'll have stuff. If there's a wire in between stuff, that means that, I need those things connected in the same row. Y'all think y'all can do it? I think you can do it. I know you can do it. All right. That's it. Y'all pray that this actually recorded and streamed.